This is lesson 61 of the quantum mechanics mini lecture series, derivation of the Schrodinger equation. So having talked about operators, I can now derive one of the most important equations in quantum mechanics, the Schrodinger equation. Let's first consider a closed system, in other words, a system that's isolated from the world. Let's take some object, like an electron, put it in like a box, and at time t is in some quantum state. Okay, written as follows: psi at some point time t. Okay, and one of the basic ideas of quantum mechanics is that if you know the state of a system at one time, then quantum equations of motion tell you what it will be at some later time. And we can take the initial time, let's call it psi naught, I should say psi. So this is the state of the quantum system at the initial time t equals 0. Okay, put in 0 for t, and some later time psi of t, right? So we can rewrite this. We can write this as follows: psi of t. So at some final state, the state of the quantum system at some later time t, you can write it as some unitary acting on the initial state. Okay, this is also called the time dependent operator because it depends on time. It's got a t in it. Okay, that's what allows for the quantum state to evolve with time. So let's take the time evolution operator for some small infinitesimal epsilon. Okay, some infinitesimal, some small amount epsilon. We'll make use of the following relation for unitary operators. We're going to assume that the time dependent operator is unitary, which means that it'll satisfy this. Okay, this is called epsilon, Greek symbol epsilon. Okay, for some small time interval. So we can also note that u hat of t is close to the unit operator I. Okay, it's sort of like multiplying by 1, but it differs from something of order epsilon in this case. So therefore we find that u epsilon is I minus a small amount, epsilon h hat. Okay, and note that the Hermitian of this is just the following. We've just put a plus instead of the minus for the I, h operator, h dagger. Okay, that's the Hermitian adjoint. Okay, and h is like an energy operator. H is also known as the Hamiltonian. Okay, like the energy. So it differs. The unitary operator differs by a small amount from the identity operator by this thing here. Let's now substitute these two expressions into here. And we'll get the following: I plus I epsilon dagger equals that. Let's expand the parentheses. Whoops. This times this, minus that times that times this, minus that times that. So I get I times I minus I times I epsilon h plus this. Okay, very messy. But we can simplify this, right? We can break it down. That's pretty much 1. If you clean that up, you get this. Simplifies to this. Okay, and this basically means that h is both Hermitian and unitary. Okay, meaning that it's also an observable. Okay, it's the observable for the energy of a quantum system. It's called the Hamiltonian. Okay, an observable is a measurable property of a quantum system. Okay, where h is the energy observable, also known as the Hamiltonian. Okay, in the next video I'll show you how to get the Schrodinger equation using these steps.